should be able to verbalize.
Okay.
It's something we started today. And it's derivative. We talked about this for a second last time, but not for very long. It's derivatives of logs and exponentials.
Okay.
And yeah, we spent the whole day on the lesson for it, but I was still pretty confused by the end.
Well, the best way to clear up confusion is to try to do some problems.
Yeah.
So what problems do you have?
So I have my homework pulled up, and there's plenty of problems on there.
All right. Let's start with some of them.
All right, so yeah, again, just like they have been, all these are just like they give you a function
and they ask you to take the derivative of it, right?
Right, exactly.
Okay. Give me the function.
All right, so it looks like we have 7 ln of 16x.
Is that it?
Yes.
Okay.
Except there's parentheses around the 16x, but I don't know if that matters.
Yeah, I knew that. I guess it does matter. It's always good to put the argument into the parentheses.
Mm-hmm.
Take a simple one. What's y prime? You have to just memorize this.
I should know that, but I forgot.
1 over x.
That's right.
Okay. So when we're analyzing, if I said, what's the derivative of 6? Here, if I said y was the natural log of 16x, what's y prime?
1 over 16x
times the derivative of the inside. You have to apply the chain rule here.
Oh, that's right, yeah.
It's the derivative of the inside.
16.
Yeah, notice something really interesting happens.
Oh, okay, and then it turns into 1 over x.
So it doesn't matter if there's a coefficient in front of the x.
Okay.
But still, you have to apply the chain rule. Okay?
Mm-hmm.
So this one, the 7, you can just treat as a coefficient. You don't need to apply the product rule or anything like that. It's just 7 times 1 over 16x times 16, which gives you 7 over x.
Okay.
What else?
All right, so the next one is 2x to the 4th ln x.
What rules do we have to apply to this one?
Power rule and chain rule.
Just the product rule. There's a multiplication taking place there. And because you're multiplying a polynomial by a log function, the only way to do it, you can't do this algebra. That's as simple as it gets, simplified as it gets. So I have to do the product rule. I have to consider that one of these is u and the other one is v. And if y equals uv, what does y prime equal?
U prime times v plus v prime times u.
Okay, so let's do this. What's u prime?
That would be 8x cubed.
What's v?
ln x.
And now what's the derivative of v? What's v prime?
1 over x.
Times 2x to the fourth. So this does simplify a little bit. And you could factor out a 2x to the third if you so wished, but I don't know that it's necessary.
Okay.
I don't factor stuff out unless it leads to a simplification.
Mm-hmm.
Factoring this out does not lead to a simplification. It just leads to this. That's not simplified.
Right.
If I had a denominator that had a x in it or something, well, then I would be able to simplify it by factoring it out. But if you can factor but it doesn't simplify, then my rule is don't factor.
Okay.
If you can factor and it allows you to simplify, then factor. What else you got?
This is looks like ln of sine x.
What rules are we going to use?
Chain rule?
Just the chain rule, exactly. So what's the derivative of the outside?
1 over x.
Mm-hmm. First of all, to figure out the derivative of the outside, you need to figure out what the inside is. Let's let the inside be u. What is the inside?
Sine x.
So what I really have is y equals natural log of u. Well, the outside is dy du. So y prime is 1 over u, but now I got to take it times the derivative of the inside. What's u prime up here?
Cosine of x.
So this answer becomes 1 over u was sine x, times u prime, which is cosine x. That's cotangent x. That's the answer.
Okay.
The only thing we had to apply was the chain rule. The derivative of the outside. Whenever you're doing the derivative of the outside, do not change the inside. In other words, it's 1 over sine x is the derivative of the outside. Now, it's not always necessary to do that up there. As long as you know what the inside is, then you don't have to do this step. Is all you have to do is apply the derivative of the outside times the derivative of the inside. Well, the derivative of the outside is 1 over sine x. I do not change that. That's always my denominator for the derivative of the outside. And if it was super complicated, it would be like that. Let's say I had something like y equals natural log of x squared minus 2x plus 1. What's the derivative of the outside?
1 over x squared minus 2x plus 1.
Yeah. And the derivative of the inside is 2x minus 2.
Okay, so whenever you have the ln on the outside, it's always 1 over and then the inside. 1 over what the inside is.
Exactly. Now, I made this problem up out of thin air, but I happened to notice something. What can I do to simplify that? Is it? In other words, it is.
Factor
This
back to the
lose
bottom.
points if you gave that answer. So factor
Right.
the numerator.
2 times x minus 1.
Factor the denominator.
X minus 1. Oh, okay, yeah, that's x minus 1 and x minus 1.
So that cancels with that, and I end up with just 2 over x minus 1. Well, that's a whole lot simpler than that.
Right.
So in this particular case, factoring helped a lot because it allowed me to cancel something from the numerator and the denominator. It was purely accidental. I didn't design the problem that way at all, but this actually was a pretty good example of a problem where you have to keep looking at it. In other words, that's not a final answer, but you don't know it until you try to factor it. In other words, it's only after I looked at it that I realized I was going to get an x minus 1 in the numerator, and I was going to have an x minus 1 in the denominator also.
Right.
So I was able to simplify it. If I made that 3 instead of 2, then that's the final answer, 2x minus 3 over that denominator. I can't simplify it. There's no way to simplify it. Okay, what else you got?
All right. 1 second. Okay, so we have ln and then x plus 4 over x minus 4.
Like that?
Yes.
It's the derivative of the outside.
X minus 4 over x plus 4.
Good. In other words, it's 1 over that, which turns into the reciprocal.
Right.
So that's the derivative of the outside. Now what's the derivative of the inside?
So we'd have to use quotient rule for that, right?
Yep. What's the rule?
It's the bottom
Start
times
bottom.
right.
Start with the bottom and end with the bottom squared. That tells you all you need to know. So start with the bottom.
So it's x minus 4
times
just 1
minus
x plus 4
times
1.
Okay, all over
X minus 4 squared.
Okay, and let's write that like this, because I can see I can cancel one of those x minus 4s with that one.
Right.
So what do we got? Let's see, if I multiply this out, the x's disappear. I get a minus 4 and a minus 4, so I end up with minus 8 in the numerator. And then down below, I end up with an x plus 4 times an x minus 4. There's your answer. Now, the same rule applies is if you get an answer that it's in factored form, don't necessarily multiply those two things together. It does not progress the problem. It doesn't simplify it. It doesn't do anything. And in fact, sometimes it makes it worse because I never know what I'm going to do with this answer. What if somebody said, well, you got to multiply that answer by x plus 4? Well, then I would want this in factored format. I wouldn't want it in a polynomial x squared minus 16. So the same principle kind of applies, is if you have an answer in factored form and you don't really improve things by multiplying these two together, don't do it. Leave it in factored form. I prefer answers in factored form because I never know what the next step's going to be. And it might be a step that I needed in factored form. Makes it easier to do the next step.
Right.
What else?
Oh, also on that last one,
Mm-hmm.
it also said determine the intervals on which the results are valid.
Okay. Well, which points don't work very well in our answer?
Sorry?
In our answer over here, what values of x can I not have?
-4 or +4.
Uh-huh. That would cause division by 0. So automatically, it cannot have values of x that are either of those.
Mm-hmm.
Now, furthermore, I can't have the argument, which is x plus 4 over x minus 4. That's the argument of the log function. Well, we know that has to be greater than or equal to 0. It can't even be 0. So I would not be allowed to have x minus 4 as an answer. And this has to be positive. Now, you know how to do a sign chart? When you have a quotient like this, and it's an inequality, and 0 is always on the right side, the only way to really solve it that I know of is a sign chart. So I'll show you how to do it with a sign chart, and it'll probably ring some bells, because there's no way to solve this problem without a sign chart. Okay? The first thing I got to do before I can get a sign chart is find the critical points. What are the critical points of this function? And that means wherever the numerator is 0 or the denominator is 0.
Be -4 and 4.
Okay, now I draw a line chart. Not an XY coordinate grid, but a line chart. And I put the two critical points on there only. I don't even want 0 on there. Now, pick a point to the left of -4.
-6.
Okay. Is the numerator positive or negative when x is -6?
Negative.
The denominator positive or negative?
Negative.
Therefore, their quotient is positive. So everything to the left of -4 is positive.
Okay.
Now pick a number between -4 and 4.
0.
You'll notice that everything between -4 and 4 is negative.
Right.
If you pick a number to the right of 4, you'll get positives again. Well, the only allowable domain for a log function are positive numbers. You certainly can't have negative numbers, and you can't have 0. So if I wanted to give you interval notation for this, it would be -infinity to -4, parentheses, in combination with 4 to positive infinity. That's our domain, and that's what they're asking for with the second part of that question. Over what intervals does this problem make sense? Well, if I'm outside of these two intervals, the problem doesn't make sense because I'm taking the natural log of a negative number or 0. And you cannot have it be -4 or +4. Because either one of those would not make it greater than 0. It would make it 0.
Right.
So it's got to be greater than 0. The restrictions for the domain on the log functions are worse than square root functions. I have a square root of x, then x has to be greater than or equal to 0. But if I have the natural log of x, x has to be greater than 0, not even equal. So this has a more restrictive domain on it than that. But this line chart is the only way I know to solve that problem. It's very hard intuitively. And another problem that would be difficult is if I had x plus 4 times x minus 4, and that was, say, less than 0. Well, figuring out what values make that less than 0, the only way I know how to do it is by using a line chart. You figure out the critical points, you put them on your line chart, you test left and right, and the moment I test to the left of -4 and get a positive value, I know that everywhere from -infinity to -4 gives you a positive value. So that's the beauty of a line chart. It's not like I have to figure out every point on the line chart. I just have to test to the left of my critical points, to the right, to the left, to the right.
Right.
In other words, what they were really asking on that question was, what's the domain? I think. Actually, it wasn't just what's the domain. In other words, here's the problem. The domain of that would be what I just put, -infinity to -4 and +4 to +infinity. Once we take the derivative of it and we get this over here, well, that domain's a little different, but not really. In other words, the domain restrictions of the original function apply to the derivative. So I can't look at the derivative and merely say x can't be -4 or +4. I still cannot have x anywhere between -4 and 4. In other words, looking at the derivative, it looks like x could be 0, right? Be 1/2 if x were 0. So x being 1/2 does not violate that a bit, but it sure violates that, because now you're having to take the natural log of a negative number. So you got to be careful when they ask about the domain. They're not really asking you about the domain of the derivative. They're asking you about the domain of the original function. Now, if after you take the derivative, it introduces even more restrictions, then the derivative would have some domain restrictions. I'm not even sure how that works, to be honest with you. I guess you can say the domain of the derivative. Actually, I don't know. I really don't know. I've never seen a question like that, so.
Hopefully I won't.
Yeah. Well, that was hard enough, because that one required you to do a line chart. Let me just test you on that. Tell me the solution to that. That is true.
You have to find the critical points.
What are they?
-1 and 5/2.
Okay. Next step.
Just plugged in.
Draw
Say
a line chart.
That's right.
And label those 2 points only. Don't put 0 on there because that tends to confuse the issue. If I put 0 on there, it looks like a critical point, and it's not. So to the left of -1, pick the closest whole number you can get to the left of -1.
-2.
Okay, what's the numerator when I plug in -2?
It's going to be negative.
What's the denominator?
It's going to also be negative.
So this whole area here to the left of -1 is what?
Positive.
Okay. Now pick a number between -1 and 5/2.
0.
Gives you negative numerator, positive denominator, negative in that whole area. Pick a number to the right of 5/2, becomes positive. What is my solution set?
It's negative infinity to -1.
Parentheses or bracket?
Would be parentheses.
If that was greater than or equal, it would be bracket.
Right.
But it's not. It's greater than only. Oh, man. I don't know what happened here. What the heck? I must have hit something I wasn't supposed to hit. So, combination with what?
5/2 to infinity.
And again, parentheses everywhere. If I make that greater than or equal to 0, then that becomes a bracket because at -1 it is, oh no, that's still a parentheses. It can't be -1 because we can't divide by -1. So that's still a parentheses, but this becomes a bracket. Sometimes I hate Windows 10. I really do hate it. It pops open all these windows whenever you get down near your taskbar.
Yeah.
If this was the problem, then this would be a bracket. Because it actually could be 5/2, right? In other words, when x is 5/2, the numerator is 0, the denominator is not. That is greater than or equal to 0. So this would still be parentheses because x can't be -1 because I can't divide by 0. But the other side would be bracket. That actually was a pretty good problem to change it to greater than or equal because it's a little bit of an unusual solution. But that determines usually whether you can have brackets or parentheses as to whether that's a greater than or equal. But even with the greater than or equal, this had to be a parentheses because I can never divide by 0. So x cannot be -1. All right. What else we got?
This next one is just 11 to the power of x.
All right. What's the derivative of e to the x?
It's e to the x.
When you have a number other than e, the derivative is 11 to the x times natural log of 11. Now, I got to check that in the book because I don't do it that often that I'm not 100% sure. So I'm taking the derivative of a to the u. Do you have a calculus book?
Not, well, we have one that's kind of online.
Okay. The calculus book I have, the inside cover has all your derivatives and integrals of all of the ones you're supposed to memorize. So it's really good. But
Okay.
what it says is if I have a to the u, then the derivative of a to the u with respect to x is going to be natural log of a times a to the u times u prime. It always assumes there's a chain rule in effect here. But in our case, this was an x and that's an x. And notice that's what I did. A to the x was 11 to the x. The natural log of a was natural log of 11. So it's very similar to e to the x. The only thing you have to do is add natural log of e. And in fact, you'll notice that that works even on the e to the x. In other words, this formula works on e to the x because the natural log of e is 1.
So it's just 1 times.
Yeah. So this is actually the general formula for all exponential functions. Whenever your variable is in the exponent, you can use this formula down here. It's natural log of the base times the base to the x power.
Okay.
Okay, what else?
This next one's pretty similar. It's just 3 to the x, but it's times 7.
Okay. 7 is just a coefficient. Again, you don't need to use the power rule. In other words, if I told you y was 6x to the 8th, you wouldn't use the power rule. You would just start by multiplying that by that. And you get 48x to the 7th, right? Well, we're going to do the same thing over here. In other words, it's going to be 7 times what?
X.
3 to the x times natural log
of 3.
That is the derivative of that. And the 7 just goes along for the ride.
Okay. So you don't have to do product rule for that?
You have to do product rule. Notice that we could do product rule.
Oh, but it would do the 7 just be 0.
Same thing, because you get 7 times 3 to the x natural log of 3 plus the derivative of 7, which is 0, and I don't care what's to the right of the 0, that goes away. So even if you mistakenly thought you needed the product rule, you get the same answer.
Right.
And therefore, you don't really ever need the product rule when you just have a leading coefficient like that. What else, Chris?
This one is 7 times log base 4 of x to the 4th minus 3.
All in the argument?
X to the 4th minus 3 is all in the argument, yeah.
Okay. Let's take the simple function. How do I take the derivative of that? Now, remember that if this was natural log of x, the derivative would be 1 over x. So it becomes it's 1 over natural log of 4 to the x, like that. Or actually, I should write it like this. It's 1 over x natural log of 4. In other words, you do kind of the same thing as you would with natural log of x, but in the denominator, you add the natural log of the base. Similar to the way we did the previous ones, where we multiply by the natural log of 4 when we're taking the derivative of an exponential function. When we're taking the derivative of a log function that's not natural log, then it's 1 over the argument times, in the denominator, the natural log of 4. So let's do that. So the 7 stays where it's at. What is the derivative of the outside?
1 over ln 4 times the inside.
What do we need to finish this problem? Got to apply the chain rule.
Right.
So we got to multiply everything by the derivative of the inside. In other words, all this is the derivative of the outside. But we have an inside. What's the derivative of the inside?
4x to the third.
And there's your answer. Well, answer is 28x to the third, all divided by x to the fourth minus 3 times natural log of 4. Remember, that's just a number, natural log of 4.
Right. So are you supposed to put the
which one
x
first?
Minus 3.
The problem, usually numbers go in front of polynomials, right? In other words, this would be the standard way of doing it. The only problem with writing it this way is that somebody can confuse that for the whole argument. So I tend to write it x to the fourth minus 3 times the natural log of 4, and that cannot be misinterpreted.
Okay.
Because there's no argument after the 4. Whereas if you put something else after the 4, you better be using your parentheses properly. I would have to put a parentheses after the 4, another parentheses, x to the fourth minus 3. So I think either one of them is correct. I'm not sure one is more correct than the other. I prefer writing math stuff so that it has the least chance of being misinterpreted.
Right. That's probably a good way of doing it.
Let's just review, because this is important, I think. If I have, excuse me, let me review starting with something else. If I have an exponential function, 11 to the x, well, then y prime is 11 to the x times natural log of 11. If I have a log function, log base 11 of x, well, now y prime is, we know it's 1 over natural log of 11 times x. So notice that when we take the derivative of exponentials, everything's in the numerator. When we take the derivatives of logs, everything's in the denominator. For the outside, at least. And that should be one way of helping you memorize it. In other words, if y is equal to some a to the x, then y prime is what?
a to the x times ln a.
Good. And if y was equal to log base a of x, what's y prime equal to?
1 over x times ln a.
Perfect. Those right there, that's, if you can memorize that, do so. It's not so easy to do. I've been tutoring calculus for 8 years now, and before this session I did not have that memorized, but I do now. And the key is when you're doing exponentials, put everything in the numerator. When you're doing logs, they all go in the denominator. The reason it's kind of hard to memorize is because the next thing you're going to study after differential calculus is integral calculus. And so you go the other way on these things. And so there's actually 4 combinations. There's the integral of a to the x, and there's the integral of natural or of log base a to the x. And each of those is different also. So you actually have 4 things to memorize when you're dealing with exponential functions or log functions. The ones that are really easy are the natural logs. Notice that that's the easiest one of all. In other words, if y equals natural log of x, then y prime is just 1 over x, I could say, times the natural log of e, but that's 1, so I don't need to. So natural log is the log of calculus.
Right, okay.
Natural logs 10 times more than you'll use logs of a different base. And it is because the derivative of natural log is 1 over x. That's the reason. That makes the integral of 1 over x natural log of x. So natural log ends up being huge in calculus for virtually everything you do from here on forward. And you almost never run into log base 10 or log base 4 or any of those. You can handle them with these formulas that we've talked about today, but it's just you don't run into them very much. Everything is natural log in calculus almost. That's why I don't even have those others memorized. Because you don't run into them very much. I had to have my book open on the inside cover and look at it. What else?
This next one is kind of what we were doing. It's log base 8 of x.
And what's the derivative?
Should be 1 over x times ln 8.
Perfect. If I made it x squared, what would it be?
Don't know. What would it be?
Well, what would it be? Start with the derivative of the outside.
That's what we just did, right?
That's the derivative of the outside.
Okay.
What we did before was 1 over x. This is 1 over x squared because the argument is x squared.
Right.
Now I have to apply the chain rule and multiply everything by the derivative of the inside, which is 2x. So the x's cancel, and you end up with 2 over x times natural log of 8. So that is the derivative of this one because the chain rule. The chain rule is the only difference. When I'm taking the derivative of the outside, I use exactly the same formula as I use for this. It's 1 over the inside times natural log of 8 in the denominator. But then you have to multiply it by the derivative of the inside, which is 2x.
Okay.
So whenever your argument is not x, then you're always going to have a derivative of the inside, unless it's something like this. If I had this, what's that answer?
Same thing, but replace x with x minus 1.
So it's x minus 1 times natural log of 8. I still actually do have to apply the chain rule because there is an inside, but what's the derivative of the inside?
Just 1.
Yeah, so I kind of ignore the chain rule with a problem like this. However, if I made that 2x minus 1, now the derivative of the inside is 2, and I'd have to put a 2 up there.
Right, okay.
So really the only thing you have to do is memorize these special derivatives, like derivatives of natural logs, derivatives of logs, derivatives of exponential functions. And that covers pretty much everything. In other words, if you can take the derivative of that, this, and this, you're home, you're in business. And you have the 4 ways to take the derivatives of all 4 of those. You know them, or you want me to go through them? I think you know them.
Sorry? Yeah, I think I'm
pretty
pretty good.
These 4?
Yeah,
that's
I think so.
To the x. This is 7 to the x, natural log of 7. This one is 1 over x, and this one's 1 over x times natural log of 17.
Right.
And that's the derivative of the outsides. Now, if you have an inside, you're going to have to apply the chain rule. But the main thing to memorize is the formulas for the outsides. Because, I don't know, they're just tough to memorize. At least they always have been for me.
All right, well.
They try to teach you calculus without even giving you a calculus book. It's an online book.
Right, yeah.
Is it a full online book? Is it like a textbook, only just online?
Kind of. It's not. I'd still prefer just a regular book.
Well, for calculus, for sure. Me too. If I was learning calculus from scratch, I would want a textbook. I would not want to have to do it from an online book. There are just too many times you have to go back and review. Plus, your textbooks have these neat little things like inside page gives you all your basic differentiation and integration formulas. In other words, the ones we just covered are all on the inside cover. So if I ever forget one, I just open the first cover of my book and there it is. What else? We got 5 minutes here.
All right. This one's a little different.
Okay.
It's e to the y times y to the e.
And this is not, we're going to call this f of y instead of y. Because our variable is y. Okay. So I can't use y on the left. But I can use function notation, f, but it's not f of x. The variable on the right is not x, it's y. So I kind of hate it when they do this. I would prefer them to use a variable like z.
Yeah.
Because it's easy to confuse students with this y, thinking that that's the same as f of x. It's not.
Yeah, I guess we could write it as
We could,
something else.
but as long as you're aware of it, we'll leave it as it is. What
Okay.
we have to use?
Product rule.
Okay.
So we have e to the y times how would you do that? The y to
I
the
don't
e.
know which way you're doing it. Part of the problem with the product rule is it can be u v prime plus u prime v, or it can be u prime v plus u v prime. In other words, I
Right,
can do
yeah.
these in either order. And part of the problem I have with students is I don't know which order they're doing. So when you get that first term, guess what? That is both u and u prime. So I still don't know which order you're doing it in. What I usually tell students is always use this. And the reason is that it lets you get started without any work. You don't have to figure out how to take the derivative of anything to write u. So I actually much prefer that to what's below it, even though they're the same. It just allows for easier communication with myself and the student. Plus, I think it's easier as a student to do it. Because what I find is that most people, they don't know where to start because they have to figure out, well, which one can I differentiate easier, right? Well, forget that. Just start. There's u. Now, what's the derivative of that? That is a power function. That's it. You can use the power rule.
So
E is a number, in other words. If I said, what's the derivative of y squared? You'd have no problem.
So it's EY to the power of E minus 1?
Correct. That is this part here. Now, the second part. What is u prime?
Still E to the Y.
And v?
Y to the E.
There's your answer. Now, again, I can see some stuff that I could factor out. I could factor out an e to the y, but it doesn't really help. But if, say, I had a denominator that had an e to the 2y, well, now it would help a lot factoring out that e to the y, because I can reduce the problem. But if there's nothing in a denominator, then there's no point in factoring the e to the y out. You don't end up with anything that can be simplified. And there's nothing you can do with that and that. Think of this as being y squared and y cubed. You couldn't do anything with them. Even if the exponents are one different, that's all it takes before you can't do anything with it. I cannot add y cubed to y squared. Just like I can't add y to the e minus 1 to y to the e.
Right, yeah.
Only thing I can do here is to factor out an e to the y, which you could do, but it doesn't make it any simpler. All right, Chris, you got any final questions? I was a little bit late, so I feel like I should give you a few more minutes. If you have any final questions, we can certainly cover it.
We went through pretty much all of it, I think, and the rest of it is just problems that are very similar to ones we've done, so I think I'm okay, actually.
Yeah, I think you're okay, too. I think you know how to do every one of these, to be honest. If we were to go back and do every single one we've done, I have no doubt you'd be able to do each one of them correctly.
All right, I hope so.
All right, Chris. I will talk to you next time. You have a good week.
Sorry?
I said I will talk to you next time. You have a good week.
You're cutting out a little bit.
Okay. I said I will talk to you next time.
Okay. All right.
All right. Bye-bye.
I think we got this next Wednesday. I think it's the same time.
Okay, cool. Talk to you then.
All right.
Bye-bye.
I'll